Hello, Math 1224. This is Dr. P with Lesson Launch 14.1, Series Finale. No, this is not the last video that I'll be producing. It's just a cute title for this particular video. So I wrote down this sequence definition. A sub n equals 1 over n times n plus 1 for n greater than or equal to 1. That is called a sequence. It is an infinite list of terms where each term is a real number. So that's a sequence. In this video, we're going to talk about an example of a series. A series is gotten by adding terms of a sequence together, either finitely many or infinitely many. So gotten by adding. I found that, I don't know what it is with tablets, but it's harder for me to write and talk at the same time on this device. Terms of a sequence together. And this could be finite or infinite. All right, so an example of a finite series might be something like let's see, I could write down, for example, this finite series, a1 plus a2 plus a3 plus a4. And using this definition, I would get, this would be equal to, let's see, let me move that down where we can all see it. There we go. I would get a sub 1, which is 1 over 1 times 2, plus a sub 2, which is 1 over 2 times 3, plus a sub 3, which is 1 over 3 times 4, plus a sub 4, which is 1 over 4 times 5. All right? And then I could calculate what that is. That would be 1/2 plus 1/6 plus 1/12, that's a 1/6 there, plus 1/20. That's going to come out to, let's see, I'm just doing the math mentally here. I think actually, miraculously enough, that comes out to a nice even 4/5. Anyway, we'll talk more about that later. But that's an example of a finite series. It's gotten by adding some of the terms of this sequence together. By the way, another way that we can represent that would be s sub 4, which is equal to the sum from I equals 1 to 4 of a sub I. Okay, I believe we talked about this notation briefly before. This is sigma notation, and this means, let me just write this down, that means add up the term a sub I for I equals every integer from 1 to 4. Just remember, when you see these numbers here, these indices, this is the first index that we use for I, and then I progresses by 1 each time until we get to that last one, which is 4. All right, anyway, so that's s sub 4. Now here's an example of an infinite series. An infinite series might look like this. I just start adding terms together, a1, a2, a3, a4, etc., and just let that go on forever. All right? And I can represent that symbolically as, well, I guess that is symbolic, but I could also represent it using sigma notation. I might call this S infinity. Oftentimes we just call this S. And that's equal to the sum from I equals 1 to infinity of a sub I. All right? So that symbol there, that sigma notation, means start at 1, add up a1, a2, a3, but this time we never stop. We just let I keep going on and on and on. And I'd like to be able to calculate this sum, but I mean, gee golly, how do I calculate a sum when there are infinitely many things to add up? That's actually the purpose of this video, is to talk about how we even think about that. All right, so this is really a video about how we think about the sum of an infinite series. So that's the, I guess I'll call that a subtitle for this, how we think about an infinite sum. How we think about an infinite sum. So I've got this sum S, which is equal to a1 plus a2 plus a3, and so on. And I would like to think about what the sum of those infinitely many numbers is. Now let's get one thing out of the way right now. If this were some different sequence, like let's say that, for example, a sub I were equal to, or a sub n were equal to n for every n. let's suppose that were true. Then what would S be? S would be something like 1 plus 2 plus 3 plus 4, and so on. And I don't think I should even expect that to have a real number as its sum. I mean, you just keep adding up integers and keep adding larger and larger integers. We don't expect that to settle down to any particular real number sum. Although there's this funny video, I think it's maybe Numberphile. It's going to be embarrassing if that turns out to be wrong, but I think there's a Numberphile video that talks about how you could think of this as being, I think it's -1/12. This is a Numberphile video. You might be interested in looking that up, but in this class, we're not going to consider that to be true at all. There's some cute reasoning that you can use to show that that might be a reasonable value for that sum, if you think it's reasonable that that should have a sum at all. Anyway, okay, I'm getting distracted here. So back to the sum, S equals A1 plus A2 plus A3 plus A. So all I'm saying is there's no reason to expect that this will necessarily have a real number sum. That's actually a very serious question, whether it should or not. But here's how we determine whether it should. So we're going to determine how to determine whether this sum converges to a real number. And then just like with limits and sequences and all the other times you've seen the word converge, if it doesn't converge, we're going to say it diverges. All right, so let me zoom that out. There we go. So here's how we determine this. What we do is we look at our infinite series, and we start writing down finite sums, finite partial sums. So for example, we write down S1 equals A1, and S2 equals A1 plus A2, and S3 equals A1 plus A2 plus A3, and so on. Now, I hope that you'll agree that each of those is a sum that we could calculate. Now, for the rest of this video, I'm going to be back to thinking of A sub n, just for this example, as being 1 over n times n plus 1. So I could calculate that S1 is equal to A1, which is 1/2. S2 is equal to A1 plus A2. That's 1/2 plus 1/6. That's 2/3. And then S3 is equal to A1 plus A2 plus A3, which is equal to, well, I know already that A1 plus A2 is 2/3, so I'll just write that down there. And then A3 is 1 over 3 times 4, I believe that's 1/12. That's going to come out to 3/4. And you might notice already there appears to be something very interesting happening with these partial sums. Again, those are partial sums. That's what we call the sum of the first k terms of the series for some value of k. We might even make a conjecture here. We might conjecture, a conjecture is just an educated guess that we hope to determine whether it's true or not. We might conjecture that S sub n appears to be equal to, I don't know, you tell me, look at these, S1 is 1/2, S2 is 2/3, and S3 is 3/4. I bet you can spot some kind of pattern there. It looks like the numerator is n, and the denominator is that plus 1, so n plus 1, for every natural number n. So the way that we think about the sum of a series is, the sum of an infinite series exists or the series converges if the sequence of partial sums S sub n from n equals whatever starting point to infinity, if that sequence converges. Now I want you to take a real critical look at this, because this might seem really fishy at first, or at least it ought to, I think. You'll notice that I'm defining the word convergence here. Now that's a really bad start. Let me try that star again. Okay, that's better. So we're defining the idea of what it means for a series to converge by using the word converge. Now here's why that's totally legal here. I'm saying that a series converges if its sequence of partial sums converges. We already have an idea of what it means for a sequence to converge. That was covered in the last lesson. So all we're doing now is we're basing the idea of series convergence, or the idea of an infinite sum of numbers, on the idea of a sequence, which we're already familiar with. And there's one more thing I want to add to this definition before I forget, and that last part of the definition is if the series converges, its sum is the limit as n goes to infinity of that sequence of partial sums. So in other words, the sum of an infinite list of numbers is the limit of the sums of all the partial lists of numbers. That is the partial list from 1 to k, as k is allowed to go to infinity. I'm actually using n here, but n, k, whichever. So in this particular example, again, for I hope the last time, I realize I'm going off on a few tangents here. So remember, I said a sub n was equal to 1 over n times n plus 1. That was the example I was using earlier. And my question was, does this sum from I equals 1 to infinity of a sub I exist? Does this sum converge? And now I have this conjecture which I could prove. I had the conjecture that s sub n was equal to n over n plus 1. So now the question of whether this exists is the same as asking, does this limit exist? The limit as n goes to infinity of s sub n, which is equal to the limit as n goes to infinity of n over n plus 1. So does that exist? And well, you can talk about that limit just by using what you know about limits from Calculus 1. What do we know about the limit as x goes to infinity of x over x plus 1? Now, you might notice I'm changing the focus here a little bit, because here I'm talking about a limit of a sequence, and here I'm talking about a limit of a function of real numbers, a function where the domain is the real numbers, roughly. But those are the same limit. Whatever this is trending to as x goes to infinity, that's going to be the same thing that this trends to as n goes to infinity. And that limit, you probably remember, we can evaluate it by using one of several little cute algebra tricks, like multiplying the numerator and denominator by 1 over x. That gives us the limit as x goes to infinity of 1 over 1 plus 1 over x. And then you just sort of glance at that and say, well, if x is getting really big, this is 1, and this is getting tiny, that's going to 0. So that limit is going to be 1. So the answer to this question is yes, the limit is 1. There we go. The limit is 1, and that means that the limit of this sequence is 1. So the main point here is that the sum from I equals 1 to infinity of a sub I, or you could also write that as the sum from I equals 1 to infinity of 1 over I times I plus 1, that is equal to 1. All right, now I'm still bothered by the fact that I've marked this as a conjecture here. And I never did anything to prove that conjecture, so I'll tell you what I'm going to do. This video is starting to get a bit long, so I'm going to stop this video here, and then in the next video I'm going to talk about how we would prove that conjecture. I was thinking about making this part optional, but actually this is something that's really good to know about how to work with sequences and series, so I think I'd like for everybody to see it. So the next video will be a hopefully shorter video talking about how we might prove that conjecture and what that means in a more general context. So see you in a bit.